Hello students, week 14 physics for grade 12. Chapter 40, lesson number 6, mass energy equivalence. Textbook page from 817 to 820. At the end of the lesson, you will be able to describe the equivalence of mass and energy. The key to understanding why a great deal of energy is released in nuclear reactions is the equivalence of mass and energy. So mass and energy are essentially the same. They are two sides of the same coin. Mass is like a super storage battery. It stores energy that can be released if and when the mass decreases. It means when there is a mass that can be used as energy. If you stacked up 238 bricks, the mass of this stack, let's say, would be equal to the sum of the masses of the bricks. Is the mass of a uranium-238 nucleus equal to the sum of the masses of the uranium-238 nucleons that make it up? Consider the work that would be required to separate all the nucleons from a nucleus. Recall that work which transfers energy is equal to the product of force and distance. Now, imagine that you can reach into a uranium-238 nucleus and, pulling with the force, remove one nucleon. That would require considerable work. Then keep repeating the process until you end up with 238 nucleons, stationary and well separated. You started with one stationary nucleus containing 238 particles and ended with 238 separate stationary particles. So, work is required to pull a nucleon from an atomic nucleus. This work goes into mass energy. The separated nucleons have a total mass greater than the mass of the original nucleus. The extra mass multiplied by the square of the speed of light is exactly equal to your energy input. So, change in energy is equal to change in mass times c square, and this is actually speed of light. One way to interpret this mass change is that a nucleon inside a nucleus has less mass than its rest mass outside the nucleus. It's very important. A nucleon inside a nucleus has less mass than its rest mass outside the nucleus. How much less depends on which nucleus. The mass difference is related to the binding energy of the nucleus. For uranium, the mass difference is about 0.7% or 7 parts in 1,000. The 0.7% reduced nucleon mass is uranium indicates the binding energy of the nucleus. The masses of the pieces that make up the carbon atom, 6 protons, 6 neutrons and 6 electrons, let's say, add up to about 0.8% more than the mass of a carbon-12 atom. That difference indicates the binding energy of the carbon-12 nucleus. So you can understand the binding energy from here. We will see shortly that binding energy per nucleon is greatest in the nucleus of iron. The masses of ions of isotopes of various elements can be accurately measured with a mass spectrometer. This device uses a magnetic field to deflect ions onto circular arcs. The ions entering the device all have the same speed. The greater the inertia, means of course mass is the measure of inertia of the ion, the more it resists the deflection and the greater the radius of its curved path. You can see the figure here. In a mass spectrometer, ions of a fixed speed are directed into the semicircular drum, where they are swept into semicircular paths by a strong magnetic field. Heavier ions are swept into curves of larger radii than lighter ones. A graph of the nuclear masses for the elements from hydrogen through uranium shows how nuclear mass increases with increasing atomic number. You can see the graph here. The slope curves slightly because there are proportionally more neutrons in the more mass atoms. Nuclear mass per nucleon. A more important graph plots nuclear mass per nucleon from hydrogen through uranium. This graph indicates the difference different average effective masses of nucleons in atomic nuclei. You can see the graph from hydrogen to uranium. This graph clearly shows the nuclear mass per nucleon. A proton has the greatest mass when it is in the nucleus of a hydrogen atom. None of the proton's mass is binding energy. The low point of the graph shows you can see the low point of the graph that occurs at the element iron. This means that pulling apart an iron nucleus would take more work per nucleon than pulling apart any other nucleus. So iron holds its nucleons more tightly than any other nucleus does. Beyond iron, the average effective mass of nucleons increases. So this is actually a kind of exemption for the element iron. For elements lighter than iron and heavier than iron, the binding energy per nucleon is less than it is in iron. If a uranium nucleus splits into two, the masses of the fission fragments lie about halfway between uranium and hydrogen. So the mass per nucleon in the fission fragment is less than the mass per nucleon in the uranium nucleus. When this decrease in mass is multiplied by the speed of light squared, it is equal to the energy yields by each uranium nucleus that undergoes fission. So the missing mass is equivalent to the energy released. That's the main point here. Energy released is equal to mass difference times speed of light square. The mass per nucleon graph is an energy valley that starts at hydrogen, drops to the lowest point, and then rises gradually to uranium. So iron is at the bottom of the energy valley, which is the place with the greatest binding energy per nucleon. Any nuclear transformation that moves nuclei toward iron releases energy. Heavier nuclei move toward iron by dividing, that is nuclear fission. A drawback is that the fission fragments are radioactive because of their greater than normal number of neutrons. A more promising source of energy is to be found when lighter than iron nuclei move toward iron by combining. There is a think question. If you know the mass of a particular nucleus, how do you calculate the mass per nucleon? You divide the mass of the nucleus by the number of nucleons in it. So if you divide the mass of the nucleus by the number of nucleons in it, you can get the mass per nucleon. Okay, a concept check question here. How does the total mass of the fission fragments compare to the mass of the fissioning nucleus? Try to answer this question. Thank you and see you next time.